Okay, so this mini lecture is going to look at Newton's law of universal gravitation. This is just going to be a real brief introduction to the idea of the law of universal gravitation, and then we're going to utilize the equation, the mathematical relationship that represents this law in an example problem. All right, so what is this idea? Well, the idea that was proposed by Newton is that any massive object has a gravitational force on another object of mass. So that two objects with mass are attracted to one another. They have a force of attraction towards one another. So if I am standing next to another person, I have a certain amount of mass, that person has a certain amount of mass, and just by sheer nature that we are massive objects, we have a gravitational attraction toward each other. Now, how come we never notice it? How come I'm not shifted towards that person and that person is shifted towards me? Well, remember, we talked about how an object behaves is dependent on the net force of that object. There are a lot of other forces acting on me depending on the situation I'm in, but most importantly is the one from the really massive Earth, right? So how much mass an object has and how much mass the second object has gives an indication of the strength of that gravitational force. The Earth is really, really massive. So the force that I feel from the Earth is really, really big. The force that I feel from the person standing next to me, it exists, but it's really, really small. And I encourage you to go look up the experiments that showed that this indeed is the case, that two objects, even objects with very little mass, have a force of gravity between them. It's kind of a cool experiment that was done. We're going to just talk a little bit about what is dependent on it. So we've already given an indication of one thing that is dependent, that influences the force. The force of gravity between two objects is proportional to the mass of the object and the other object, right? So the mass of object 1 and the mass of object 2. Okay, so the mass of the two objects, it's a force dependent entirely on the masses. So the mass of those two objects are certainly going to play a role. Much smaller force between two small masses, me and the person standing next to me, versus me and a very massive Earth mass. What else makes a difference? If I were to move further and further and further away from that person standing next to me, do you think the force between us, that attractive force, would go up or would go down? It would go down. I have much less influence over something further away from me than I do something close by. It actually goes down by a lot. The force of gravity between two objects is inversely proportional, not just to the distance, but to the distance squared. So one small change in the distance results in a much larger change in the force. All right. Now, with most relationships that are experimental, right, that we developed as the result of experiments, there is a constant of proportionality, some constant that combines all of these, relates all of these variables together. And that leads to our force of gravity. The constant is the gravitational constant, and that gravitational constant is 6.67 times 10 to the negative 11th. So it's a really small number, negative 11th, newtons meters squared per kilogram squared as its unit. So G, the gravitational constant, times, well, we know mass 1 is directly proportional, mass 2 is also directly proportional, and that distance between mass 1 and mass 2 squared is inversely proportional. So this is our relationship for the universal gravitation between two objects of mass. We're just going to do an example to use that equation. So, like I suggested, I am standing here, and let's say I have a friend of mine who is standing next to me. So I have a mass equal to 57 kilograms. My friend has a mass equal to 82 kilograms. What is the force of gravity between the two of us? What is the force I exert on my friend? And what is the force that my friend exerts on me? Do we exert different forces or the same force? Well, we're two interacting objects. I am exerting a force on my friend. My friend has to exert an equal and opposite force on me. That's Newton's third law. All right, so how do we calculate this force that we're exerting on each other? Well, we're going to use our equation. So we have the force of gravity is going to equal our gravitational constant times m1 times m2 over the distance between us squared. I forgot to mention that. We are standing 1 meter apart. Tend to forget to tell you what our distance is. That's important. All right, so then we just use the gravitational constant. 6.67 times 10 to the negative 11th. Mass 1 is 57. Mass 2 is 82. All over our gravitational constant of 1 meter. So that's 1 squared. So we get out our handy dandy calculator. And we have 6.67 times 10 to the negative 11 times 57 times 82 divided by 1 squared, which of course is just 1. And we find a force of 3.12 times 10 to the negative 7 newtons. That is a very, very tiny force. So even though that force exists, it's very, very small. We don't notice it in our kind of day-to-day interactions. All right, so the idea is that any two objects of mass can exert equal and opposite forces on each other, gravitational force. All massive objects exert gravitational forces on other massive objects. That force is proportional to the mass of those objects, and the further I get away, the smaller that force becomes in a squared inverse proportionality. All right, good job.